Welcome to the Crazy Hat Chemist. So another video here on equilibrium. Bam! Today we're doing equilibrium calculation number 5. So stay alive for number 5. Here we go. The reaction below contributes to air pollution when burned at high temperatures, above 1200 degrees Celsius, that is, where the KEQ is 1.0 times 10 to the negative 5. A sample of air, nitrogen gas, has a concentration of 0.78 molar and oxygen gas at a concentration of 0.23 molar before any reaction occurs. Calculate the equilibrium concentrations of reactants and products. So look at that KEQ first of all. That KEQ is less than 1. Therefore, this reaction is reactant favored. All right, so here's the reaction. I got 1 mole of nitrogen gas plus 1 mole of oxygen gas produces 2 moles of nitrogen monoxide gas. Okay? So how do we deal with all equilibrium problems? Mathematically, we are going to be using the process of using an ICE table. Okay, so here that is. Initial, change, equilibrium, ICE, I-C-E. All right? Now, what is the initial concentration of the nitrogen? It is 0.78 molar, so I'm going to place that right there. What is the initial concentration of the oxygen? That is 0.23 molar. That is right there. What is the initial concentration of the products? Well, again, it's going to be a 0 because the reaction has not started. If the reaction hasn't started, I can't have any of the product. So that's why it's going to be that 0 right there. Okay, now, in regards to the change, so the change of the reactants, the reactants will decrease in concentration over time because they will produce the product. And the product will increase over time. So that should tell you what the sign is in front of the reactants and the product. That is, the reactants will decrease, therefore a negative sign. The product will increase, therefore a positive sign. Okay, then we're going to look at the stoichiometric coefficients. So in front of the nitrogen, there's a 1 stoichiometric coefficient. So that's going to be a 1x, and it's going to be a negative 1x because it's going to be decreasing. And then in front of the oxygen, there's a 1 stoichiometric coefficient, and it is an x. And it is a 1x, and it is going to be a negative. So therefore, negative 1x. Now on the product side, okay, it's going to be increasing, so that's a positive. And the stoichiometric coefficient in front of the product is going to be a 2, and therefore it's a positive 2x. Now I have everything in my initial row and my change row, and now I need to come up with the sum of the two, the initial and the change. I'm going to add them up. When I add them up, I'm going to get my equilibrium. So for the nitrogen, I'm going to sum up the 0.78 minus the x, 0.78 minus x. In the oxygen column, I'm going to have 0.23 minus x, and that's what's going to be there. Then I have the 0 plus the 2x. I'm going to just have the 2x. All right? I'm going to use this information right here to solve for what I need to in this problem. Okay. Now, what I'm going to do is write the equilibrium constant expression. That is, products over reactants with the stoichiometric coefficients as exponents. Products over reactants, stoichiometric coefficients as exponents, never including solids or liquids. And of course, in this problem, there are no solids or liquids, so therefore, that's what I have. So I got KEQ is equal to the concentration of NO to the power of 2. That's an exponent of a 2, therefore it's 2, right? Divided by N2 to the power of 1, O2 to the power of 1. Now what I'm going to do is I'm going to plug in what I have in my blue circled section plus my KEQ value. I'm going to plug that all in right there. So on the left-hand side, in place of the KEQ, I got 1.0 times 10 to the negative 5. On the right-hand side, in the numerator, in place of the NO, I got 2x quantity squared. In the denominator, I have the 0.78 minus x times 0.23 minus x. Now, what we're going to do here is do a little bit of math manipulation here. Okay, I'm going to take my denominator term and move it over to the numerator of the other side. So I'm going to multiply both sides by the denominator, in other words. And I'm going to take care of that 2x quantity squared, and that's going to be a 4x squared. So bam, that's what I got right there. So now I have inside the brackets there, I have 0.78 minus x and 0.23 minus x. Remember way back in algebra when you were learning how to multiply two different things here together? You're using the FOIL method. That's first, outer, inner, and last. And the outer and the inner portions of this have the same x term, and we're going to sum that up. Okay, so we're going to take care of what's inside the brackets first because we are following the rules of PEMDAS. Okay, and there's what we got. Now what we have to do is distribute that 1.0 times 10 to the negative 5 over all three terms that are inside the brackets there. So I'm going to do that next. All right. Now what we need to do is move that 4x squared that's on the right hand side of the equal sign, and I'm going to move it to the left hand side. What will remain on the right hand side will be a 0. The other thing that I'm going to do is I'm going to rearrange all my terms on the left hand side so that they're decreasing in exponents. So I'm going to have an x squared term, an x term, and a non-x term, and that will all equal 0. And then bam, that's going to be that right there. So now I'm finally in a form of which is going to make sense. Now I'm hoping that you recognize this from actually the previous lecture. Okay, the previous lecture, which is equilibrium calculation number 4, I talked about the quadratic equation. This is also a quadratic equation. I got my A term, my B term, my C term. I'm going to plug it into my quadratic equation. I gave you a quick little way of remembering what the quadratic equation is, so make sure you watch that previous video. And here it is plugging into the quadratic equation. Now remember, with the quadratic equation, you got that plus and that minus in the front, so you're going to get two different numbers here. This is the first number, here is the second number. Since we are in chemistry, okay, that means that one of these numbers isn't going to work for us. If we were just in your regular math class, then both numbers would be equally valid, okay, because they are valid numeric values for solving of the quadratic equation when solving for x. However, in chemistry, we cannot have negative concentration, so the negative value, we're going to get rid of that one all total. Okay, now, before I plug this into my equilibrium section there and solve for the nitrogen, oxygen, and nitrogen monoxide concentrations respectively by using what's inside that blue oval there, I'm going to do one other thing. This was a lot of math and a lot of steps to do along the way. And this method works all the time, no matter what. It is both accurate and precise, and it is the right way. However, there is an alternative path of which you can take if you understand something that's going on here. Okay, and here is the concept. What I did is I plugged back in everything into the KEQ expression before doing all the math. Okay, so looking at that. Now, the other thing here is that we really need to look at this concept, and that concept I'm going to write down right here for you. And this is the important concept. So if the value of x is small, that is so small that an approximation can be used, then we can use the approximation because we're using significant figures, and it does matter. So the approximation is as follows. So follow this concept. I got 0.78 minus x. Let's pretend that x is really, really, really small. If x is really, really small, then 0.78x minus whatever that x value is going to equal 0.78. Okay? If that is the case, I'm going to get rid of the minus x term because x is so small that it doesn't affect the value of 0.78. Then I'm going to ask myself the same question. If 0.23 minus x, and if the x is so small that it doesn't affect the 0.23, I'm going to get rid of the minus x term. Okay, and there's going to be a rule here for this, and I'm going to tell you what the rule is. There are two different methods of using this rule. One is the 5% rule, and one is the 100 times the k rule. Okay, I'm going to use one of these rules in particular. But having said this so far, let's figure out if this actually holds true. If x is really, really small, then when I solve for x, because there's still an x in this equation, when I still solve for the x that is remaining in this equation, I should get a value that's very similar to the yellow value that I got here using the quadratic equation. So we're going to take the 0.05, the 1.0 times 10 to the negative 5, the KEQ, times 0.78 times 0.3 divided by 4, and then the square root of that. So I'm solving for x. Okay, that's what we're doing right here. So I've gotten rid of those x terms, and I'm going to solve for x. So x is going to equal 6.7 times 10 to the negative 4. Now that yellow value of 6.7 times 10 to the negative 4 has two significant figures. There are two significant figures in this problem, and that number 6.7 times 10 to the negative 4 should look very similar to this one right here. In fact, it is the same number using the correct number of significant figures after rounding. So that means that the x is really, really small. Okay, since the x term is really, really small, I can use the approximation. So what is the rule on how do I figure out if I can use the approximation, or do I have to go through the whole entire quadratic equation? Here is the rule. The rule is as follows. If 100 times the k is less than the initial concentration, then you can use the approximation. The other rule is the 5% rule. You got to figure out which rule you want to use. I like this one. Most of my students find this one the easiest one to use. So I'm going to apply this here for you and make sure that you understand it. So 100 times 1.0 times 10 to the negative 5 is 1.0 times 10 to the negative 3. Is 1.0 times 10 to the negative 3 less than 0.78? If that's the case, I did correctly, got rid of the minus x term. I'm going to ask the question again. Is 100 times 1.0 times 10 to the negative 5, which is 1.0 times 10 to the negative 3, is 1.0 times 10 to the negative 3 less than 0.23? If the answer is yes, then I'm going to get rid of the minus x term. And therefore, I am going to solve for x, getting rid of those two minus x terms in the denominator, and I'm going to get the 6.7 times 10 to the negative 4. Perfect, it works. That is a fantastic thing. Okay, now what we're going to do, now that we actually have our value for x, whether we use the quadratic equation or we use the approximation, it doesn't matter. Now we're going to solve for the equilibrium concentrations of nitrogen, oxygen, and the nitrogen monoxide respectively. Here we go. So we're going to plug it in to the equilibrium section there. So for solving for the nitrogen, we got 0.78 minus 6.7 times 10 to the negative 4. Now, using significant figures, the 6.7 times 10 to the negative 4 is such a small value that we get 0.78. This is actually validating the fact that the x value that you solve for is so small that it doesn't matter. Okay? Because you get right back the 0.78. Let's solve for the oxygen concentration. Here it is right here. 0.23 minus 6.7 times 10 to the negative 4. That's equal to 0.23. Again, that's equal to that same value because I'm using two significant figures. Okay, and this is also reaffirming that x is so small, x is 6.7 times 10 to the negative 4, and it's so small, then when I subtract that from the initial concentration, that I get the initial concentration back again. Fantastic. Now, of course, this won't happen with the nitrogen monoxide concentration because x is x and there is no initial concentration. It's just 2x. Okay, so I'm going to plug in the value of 6.7 times 10 to the negative 4, multiply that by 2, and then this is what I get right here, and that is 1.3 times 10 to the negative 3. Okay, all these concentrations are in molarity. Okay, and you should actually be able to plug these values in, get back the KEQ for you as an approximation. Remember, you have made some rounding here because we are dealing with two significant figures. Okay, this tells you how to use the approximation. If 100 times a k is less than the initial concentration, then use the approximation. Don't use the quadratic equation, although you can always use the quadratic equation. In college, I've had to use the quadratic equation many times, but on the AP chemistry exam, I've never had the College Board use the quadratic equation because they're not testing you on how to use the quadratic equation. They're testing on you if you know how to do the problem and set it up correctly and use the approximation. All right, hopefully that works out well for you. I am the Crazy Hat Chemist, and I got another hat here for you, okay? Oh yeah, give me a thumbs up if you like that video, subscribe to my YouTube channel, look for me online and find my website. There's lots of cool stuff there. I will see you next time. Bye for now.